So we've been looking at probability of single events, then we looked at the probability of compound events. And so today we're going to look at something called conditional probability. In other words, the probability of events when some requirements have to be met. Okay, that's what conditional means. So let's go ahead and define that officially. So conditional probability is the probability an event will occur given that another event has already occurred. And you're going to see this phrase given that quite a bit today. So maybe a good example, since it's raining today, the probability that it will rain today, given that it is cloudy. Okay. So notice I'm asking you to find the probability that it would rain today, but we're saying that cloudy has already occurred. Okay? And of course, does cloudy possibly have something to do with the fact of whether it might rain today or not? Yes, right? So not necessarily that one causes the other, but I think that the probability of rain is heightened, right, when it's already cloudy. Okay. So that phrase, given that, is actually going to be so common in probability that we actually have a symbol for it. So when you want to state that something has already occurred, it's a bar or a straight up and down line. So when you see this right here, this literally means the probability of B given A. That's how you would say that notation there. Okay, so the bar literally means the words given that. And so this is, in general, the probability that event B will occur given that event A has already occurred. So, if we want a formula for the probability of B given A, I always try to make the bar a little taller than my letters so that it doesn't look like the letter I or anything like that. The formula is the probability of A and B both. Remember that upside down U from last time means and. Over the probability of the second thing mentioned. Okay. So this is one form of the formula, but if you were to rewrite this, so I'm going to put 2 stars by this. It's the same formula. We're just going to solve for the probability of A and B part. So it's the probability of A and B is going to be the probability of A times the probability of B given A. So all the second formula with the 2 stars is just a reworking of the first formula. And this is true regardless if A and B are independent or not. So I don't know if you remember, but when we talked about the AND formula before, I had to specify for you that A and B had to be independent for us to be able to use that formula. And so the updated formula that works no matter what we have as far as events A and B is this one right here. Okay, so the probability of A and B is actually always going to be the probability of A times the probability of B, given that A has already happened. So let's take some of our old problems and let's see if we can use this new formula. So if I wanted you to find the probability of a heart, given that it is an ace, okay, so what's the event we're trying to find the probability of? We want to know that the probability that the card in our hand, if we draw one, is the heart, right? But what's already occurred? That's kind of important to what we need to know. It's already an ace. You know it's an ace, you just don't know if it's a heart, right? So that's kind of the point, okay? So the formula, just so you know, look right here, right? It's the probability of both over the probability of the second thing. Okay, that's what this formula right here says. It's the probability of both over the probability of the second thing. So we're going to have a fraction really for each of these. Okay, so what's the probability that it is both a heart and an ace? In other words, which specific card? The ace of hearts, right? There has to be both of them. How many ace of hearts are there in a deck? Just one, right? So the probability of that is 1 out of 52. Okay, what's the probability of ace? How many aces are there total? Like 4 of them, right? So we would say that is 4 out of 52. And just so you know, when you have a fraction over another fraction and the denominators are the same, it actually works just the same as if you had a whole number on top and bottom. You can cancel those out. In other words, I end up getting what simplified fraction? 1 out of 4. Okay? Which actually should make sense to you, because if you already knew you held an ace, then you would have a 1 in 4 chance that it would be the hearts one as opposed to the diamond or the club or the spade. Okay? So let's do another one. So the probability that the card's a club, given that it is a black card. So the formula for something given something else is, again, always the probability of both over the probability of the second thing. Okay, so we're going to have two quantities. Okay, so first let's find the probability that, let's do the probability of black first, because I think that's easier. Okay, so how many black cards in a deck? There's 52 cards, and half of them literally are the black ones, right? So we could say 26 out of 52. Okay, what about both? So kind of think about that. Clubs already are black, right? So we don't really need to worry about the fact of the color. We really just need to focus on how many clubs there are, right? So because all the clubs actually are black in this case. So how many clubs are there? There's hearts, clubs, diamonds, and spades, right? So if you split the deck into 4 pieces, how many cards would be each thing then? 13. And notice again, I'm going to cancel these. Notice in this case it's actually better if I don't have a reduced fraction for these, because I really want both denominators to be 52 so that I can cancel them out. But in the end, you'll get 13 out of 26, and then at this point you can reduce it to 1/2. Okay. So again, if you think about this in another way, if you already knew that the card that you held in your hand was black, okay, then you'd have a 1 out of 2 chance that that card would also be a club, right? Because it also could be a what on the other hand? A spade. Okay. So I'm trying to do these, you know, card games aren't really our end goal here, but they're a good way to kind of introduce new probability topics. All right, so let's say I have a few events here. The probability of A is 0.2. Let's say the probability of event B is 0.9. And the probability that they both occur together is 0.1. And I want you to find two things. I want you to find the probability of A given B. Maybe leave a little space. And I also want you to find the probability of B given A. So I want to talk about how these are generally not going to be the same. Okay, so what's the general formula for the probability of A given B? It's the probability of both over the probability of which one? B, because it's the second one, right? That's the general formula. Probability of both over probability of the second thing. Okay, so what's the probability of both? I gave you all of these things. Probability of both was 0.1, right? The probability of B is 0.9. So since the decimal place is to the same spot in both of these, this actually just reduces to 1/9. Okay, think of it like multiplying top and bottom by 10, essentially. I know I'm not changing these to decimals and percentages, but I feel like you could, right? You would just do 1 divided by 9 and then move the decimal place twice. Okay, so what about B given A? Notice the top would be the same, right? Because the top is the probability of both. But what should go in the denominator since we flipped the letters? The probability of A. So the probability of both was still 0.1, and the probability of A is 0.2. So what would this reduce to if you paid attention to what we did on the first one? 1/2. Okay, so this formula is actually a little bit more useful because we don't have to worry about A and B being independent of each other. We don't have to know that fact. We can just kind of proceed with this formula. So if the probability of A and B is just plain old the probability of A times the probability of B without having to worry about the given A part, then it actually proves that A and B are independent. In other words, they don't have anything to do with each other. So I don't want to be too confusing here, but I want us to kind of talk this through and realize maybe why this is true. Also, if A and B are independent, then the probability of A given B would just be the same as the probability of A. And the probability of B given A would just be the probability of B. Okay, so I want you to write that down, and then I want us to think about why that's true. In other words, why are we not really caring about B in this case? Because A and B are what to each other? Are independent. In other words, it doesn't really matter that B occurred. Okay, so I'll give you a goofy example. Okay, let's take the rain example. So what if I asked you to find the probability that it'll rain today, given that I had Pop-Tarts for breakfast? Okay, what's unimportant about what I just said? That I had Pop-Tarts for breakfast, right? So do we really need it, or can we just drop it? We could just drop it, right? And the reason I say it's unimportant is because does me having Pop-Tarts have anything to do with the fact that it'll rain or not today? No, right? So those events, me having Pop-Tarts and it raining today, are completely what to each other? Independent, okay? So basically it doesn't matter about the first event or the second event, rather, when you're finding the probability as long as they're independent of each other, okay?
I'm going to make this really difficult, but I have a question.
Okay.
So what if you eat Pop-Tarts every Monday, Wednesday, and Friday? And then you're like, what's the probability? I mean, is
It still wouldn't have anything to do with it raining today, though, right? So just because they occur together doesn't mean they caused each other or that they had anything to do with each other. And honestly, people's misunderstanding of that leads to, incorrect stats all the time, like a lot, actually. Okay? So just because two events occur together doesn't mean they're related in any way, shape, or form. Okay? They could just have their own issues and their own probabilities. All right, so let's take this scenario. Let's say the probability of event A is 70, and the probability of event D is 30, and the probability that they both happen is 0.20. And I want you to tell me, are events A and D independent of each other or not, just based on that information? All right, so we're going to find the probability of A given D. And then we're going to try to find out if D is really important after all. Okay, so what's the formula for something given something else? Probability of both over the probability of what? The second thing, right? The thing that's already given, the thing that has already happened. Okay, we have both of these things, right? So the probability of both is 0.2. 0.20. Probability of D is 0.30. So we end up getting 2/3, which is 0.667, right? It's actually 6666 forever and ever. All right, so what you're really trying to find out is the probability of A given D then, is it the same as the probability of just plain old A was? In other words, what I'm asking you is D kind of unimportant to what A was? Okay, because notice if that's true, right, if they're independent, then that should have been true, right? The probability of A given B shouldn't have mattered, so it should just be the plain old probability of A. So notice here we get about 0.667. What's the probability of A given to B, though? 0.70, okay? So what do you notice about these? Are they equal? They're not, right? So because they're not equal, then it means you can't say D is unimportant. So you say the events are not independent of each other. What does it mean for things to not be independent of each other? It means they are what? Dependent. Okay, if you are not independent from your parents quite yet, right, it means you are somehow dependent on them. Okay, in other words, we can't make the claim that A and D don't have anything to do with each other. They probably do have something to do with each other. Okay, so in today's lesson and in Friday's lesson, we're going to use tree diagrams to kind of organize our probabilities when we want to express multiple events occurring. So a tree diagram is just kind of a visual way to express the probabilities of multiple events. So we're going to start off with some letters, but then we're actually going to look at maybe some word problems where we have to set up maybe some tree diagrams on our own. But for the first one, let's say that I give you this tree diagram. Okay, you have a choice between A or B. Okay. Notice that these two probabilities add up to what? 1, right? You're going to choose A with a 40% probability. You're going to choose B with a what kind of probability? 60%, okay? But then after you choose A or B, you can either branch off and go C or D, okay? And let's say this probability is 0.3 and this is 0.7. But then let's say you also have that same option of going C or D if you went the other way. But what do you notice about like each kind of branch of this tree diagram? Like each little unit branch adds up to what total? Adds up to 1, right? So in other words, you're making two decisions. You're deciding whether to go here or here, and then once you've made that decision, you're deciding whether to go here or here. So there's two decisions you have to make, A or B first, and then once you've decided that route, then you choose between what two options? C or D, okay? So I'm going to ask you some questions based on this tree diagram. So what's the probability that we go the A route as opposed to the B route? So just read the tree diagram. What is it? 0.4, right? That's literally how it reads, right? Let's make that part A. What about the probability of C given A? Okay, so we're going to do this one a little different because we're branching out here. In other words, we already are here. Okay, we are given that we chose A, but now I'm asking you to find the chances that after you chose A, you after that chose C, right? So what would be the probability that once you're here, you go here as opposed to here? You're just reading the tree diagram, no calculation necessary. Just 0.3, right? You already made the decision here. This is your given, right? We're already here, and the chances that we then go here would be the 0.3, okay? So what about maybe something a little more difficult? So for this one, I'm asking you for the probability that you went A, and after that also you went what? C. So the formula for A and C that we talked about today, remember, is the probability of the first thing times the probability of the second thing, given that the first thing has already happened. Okay, in other words, we're just multiplying the two probabilities together, and we actually already figured out each of those in parts A and B, right? So what did we get for the probability of A? 0.4, right? And what did we get for the probability of C after that? 0.3, and if you multiply these together, you get 0.12. Okay, so overall, you have a 12% chance of going the A route followed by the C route. Okay, just know that right now we're using letters. We're going to put some real scenarios in these in a minute. I'm just trying to get you to learn how to read the tree diagrams in a basic format first. So what if I ask you for the probability of C? Okay, so this is going to require a little bit more thought. How come? How many ways are there to get to a final result of C? Two, right? You can go which two routes? You can go A followed by C, or you can go what? B followed by C. Okay. So essentially what I'm really asking you for is what's the chances that you went A and C, or that you went B and C? Okay. So do you remember what we do for OR situations? We add the two probabilities, right? Technically, we're supposed to also subtract off the probability that we went both, but you can't go both A and C and B and C. You have to pick a route. In other words, you have to like commit to something. So we already did this one in part C, so let's just write it down. But then for the probability of B and C, you just need to follow it, right? What's the probability that we go B? 0.6, right? And then once we're here, what's the chances that we go C rather than D? 0.2. So if you add those up, this is actually 0.12 also, but you'll get 0.24. Okay, so the last and final question is, does it look like A and C are independent? In other words, are they completely separate from each other, or do they have some effect on each other? So what I'm really asking you for, I'm going to squeeze it in here. What I'm really asking you for is the probability of C given A the same thing as just the plain old probability of C? In other words, is A insignificant in this scenario, right? Would it matter what we get here? So let's look back up at our choices because we actually have both of these quantities already figured out, right? What was the probability of C given A in part B? 0.3. And then what was the probability of C given in part D? 0.24, right? And what do you notice again here? These are not equal, right? So what does it mean then? It means no, they're not independent, right? In other words, they have something to do with each other. By the way, I'm not stating what they do have to do with each other. I'm not really stating that one causes the other. I'm just saying they're not completely separate from each other. They have something to do with each other. Okay. So let's look at an appropriately timed tree diagram. I think it might be different based on numbers this year, but a lot of times politicians and statisticians try to figure out which groups of people are voting versus which groups of people aren't voting. And a lot of times they break it down to education. That's one of the biggest determiners of who votes or not. So let's say we split the population up into college degree versus no college degree. And let's say that, I think these numbers are old, but we're going to go with it. Let's say 30% of the general population has a college degree and 70% doesn't. Okay. Notice that branch in the tree diagram adds up to what, as always? Adds up to 1. So we're either going to go one route or the other route, right? And so then we're going to split up these people into 2 groups based on whether they vote or not. And let's say 80% of the college degree people end up voting, while 20% decide not to. 55% of the not college degree people vote, and 45% decide not to. Okay, so there's 2 kinds of decisions, quote, that we're making about people, right? What's the first decision we're making about people? Whether or not they have a college degree, right? Whether or not they hold a college degree. And then what's the second decision we're making about people? Whether or not they what? Whether or not they voted, right? So there's 2 events that we're kind of tracking through. Can we all agree that you're either one or the other? Like you either have a college degree or you don't, right? You either voted or you didn't, right? There's no like middle ground where you sort of voted, right? I hope not. So what is the probability of college and vote? So I'm shortening that, but I mean college degree. Okay. So in other words, I'm asking you, what's the chances that you went on the very specific path that I just said, right? So in other words, we need the probability of college, and we need to multiply that times the probability of that we voted, given that we were already in the college category. Okay, that's what the formula for something and something else is. So what's the probability that a person randomly has a college degree according to this tree diagram? 0.30, right? And then if we're already here, then what's the chances that a person that's already here decided to vote? 0.80, right? So this comes out to be 0.24. So 24% of these people both had a college degree and voted at the same time. What if I ask you for the probability of a random person being a voter, being someone who decided to vote? So how many different kind of routes are there to get to a person that decided, yes, I'm going to vote? They could have gone this way, right? They could have been in this category and voted, right? But they could have also been in what? This category and voted, right? So essentially it's the probability of college and vote plus it's the probability of what? Non-college and vote. So we already did this one, so we're not going to do it again. We already did that one in part A. But let's figure out a non-college person, the chance that they would vote, right? So it's going to be what? Not college would be 70%, and then vote would be 55%. So if you add both of those up, you get that 62.5% of people in this survey are voting, regardless of whether or not they had college or not. So what's the probability of a person not voting? So we could do that directly Or we could use some common sense and realize that I've already figured out the opposite of that already, right? Like I've already figured out that how many percentage of people are voting here? 62.5%. So what would be a really quick way to figure out how many people didn't vote then? Just subtract from 1, right? Since we're in decimal form, we'll subtract from 1. What if you were already in percentage form? Then what would you subtract from? 100%, yeah. But we're in decimal form, so this would be 0.375. Okay, so be on the lookout for things that you can find using information you already have. Don't always just jump straight to having to figure it out the long way. So the final question I want to ask you about here is, are voting and having a college degree independent of each other? So before we actually mathematically figure this out, what would it mean if they were independent? It would mean they have nothing to do with each other, right? So it would mean that you're not more likely to vote if you have a college degree or less likely. It means that your college degree would have no bearing on whether or not you decided to vote, right? That's what it would mean if it were independent. So the question it's asking is the probability of voting kind of free from any influence from whether or not you went to college? In other words, is that second thing unimportant? Okay, is the college degree important to the fact that you decided to vote or not? Okay, so we already figured the probability of voting out, right? What did we figure it was? Yeah, it was 0.625. Okay, so now let's figure out, I'm going to slide it back down. What's the probability that we vote given that we were already on the college route? So I'll slide it back in a minute. This doesn't require any figuring. It's just that you're given that you're already here. And so then what's the chance that you slide here instead of here, right? It's just 0.8. So what do you notice about this? Is 0.625 close to 0.80? It's actually not even close to the same, right? So it means they are not independent. Or what's a better way to say that so it's not like a double negative? They are dependent, yes. Okay. In other words, you are probably more likely to vote if you have a college degree, right? And that's, these stats are kind of made up, they're kind of old, but that actually is true, okay? Most college educated people vote in more percentage quantities than people who don't have a college degree. That doesn't mean anything other than we just have to educate people more about voting, right? About getting out and making your vote count. That's it. So just so you know, because we might see this somewhere, if you tend to make your zeros with a slash mark through it, I think I've talked about this semester already, but a zero with a slash mark actually means not possible. It doesn't mean zero. So if you see a zero with a slash mark, it means that the probability is impossible. It means it can't happen. Okay, so let's do maybe a couple more questions. So I want you to tell me, are drinking coffee and having pancreatic cancer are they independent of each other? And I'm going to give you some stats. Okay, if you're a coffee drinker, you certainly hope so, right? You hope that your coffee drinking doesn't contribute to the possibility that you might get pancreatic cancer, okay? So here is the stats that we're going to use to solve this problem. So out of 10,000 people, Let's say we surveyed them and 3,200 are coffee drinkers. And then of these 3,200 people, 132 have pancreatic cancer. And then let's say 160 people total have pancreatic cancer. So that's the details. So we're going to see if we can not just guesstimate, but truly tell if drinking coffee and pancreatic cancer are independent of each other. Okay, so one way to show is, does the probability of coffee and cancer equal the probability that we were a coffee drinker times the probability that we had cancer? In other words, do we not need the given notation? Okay? If we don't need the given that bar, then it means that they were independent of each other. Okay, so let's see if we can figure these out, and we have all the numbers to be able to figure out both sides of this equation. Okay? So what's the probability that they were in both categories, coffee and cancer? So notice that 3,200 drank coffee, right? Of the 3,200 people, 132 have cancer, right? So those are the people that have both, right? That are both coffee drinkers and have cancer. So this is the question, right? Is 132 out of how many total people again? 10,000? Is that the same as, okay, the probability that you were a coffee drinker by itself times the probability that you had cancer by itself, right? So how many people drank coffee? 3,200. Out of how many again? 10,000? Okay. And then how many had cancer overall out of the 10,000? 160 out of 10,000? Okay. So this is a question, right? We're trying to figure out if this is true. So if you change these to decimals, and I would suspect that you would, this one comes out to be 0.0132. And this side comes out to be 0.00512. In other words, what? They're not the same, which means they are what to each other? Yeah, these events are dependent. So notice what it doesn't say. It doesn't say like how much more likely you are to get pancreatic cancer, but what it tells you is that they have something to do with each other. Okay, you can't say that they're completely freely independent of each other. Okay, so let's look at one more where maybe we come up with our own tree diagram. We're going to use some of these type tree diagrams on Friday too. So let's say a car company produces 37% of its cars at plant A. And the rest at plant B. If 5% of the cars at plant A have a defect, and 4% of cars at Plant B have a defect. First, I want you to create a tree diagram. So tree diagrams aren't always necessary. Sometimes we'll organize our data in some other ways. But when you have more than one kind of decision to kind of go through, it is helpful. So the first kind of branch is dedicated to what? The car might come from what versus what? Plant A versus Plant B. So it really doesn't matter what letter you put on top, but makes sense to kind of go in order. What was the chance that the car was produced at Plant A? I gave you that. 0.37, okay? Which means automatically what's the chances that it came instead from Plant B since there's only two options? You could just subtract that from 1, right? But it would be 0.63. Think of like 100% minus 37%. So what's the next thing that we're kind of tracking with this company? Whether or not there was a defect or not, right? And notice there can be a defect coming out of either plant, right? So we'll use D for defect. Do y'all remember this notation, right? What does the little 1 mean? It means nothing, no, right? So this would mean defect, and this means no defect. And the same thing for Plant B, right? You can have some that are defective and some that won't be. So at Plant A, it's 0.05. Make sure you move the decimal place twice. Okay, what's implied then? How many are fine with no defect then? 0.95, right? What about here? 0.04, so how many are fine with no defect? 0.96. Okay. So then what if I asked you to find the probability that a randomly selected car that came from this company had a defect in some form or fashion, right? Okay, so how many different possibilities are there? Kind of 2, right? So we want the probability of Plant A and the defect, but the car also could have come from Plant what? B, and it also could have had a defect. So Plant A and defect, so think of it like 2 levels in the tree diagram, right? So the chance that we go A is 0.37. The chance that we then, after that, go D rather than not D is what? 0.05. And the same thing here, right? The chances that we go B are 0.63. And then the chances that after that we have a defect are 0.04. So we'll just use our calculator to figure that out, but there's actually a 4.37% chance of a defect overall. Okay. Probably shouldn't surprise us that it was between 4 and 5, right? Because one plant has a defect percentage of 4%, one plant has a defect percentage of 5%, so when you mix them together, it's something in between. Okay, I'm not sure if we'll get to finish this problem today. If not, we're going to pick it back up on Friday. But the last thing that I want to do is I want to show you that you also can organize your data in table format. So we're going to look at the number of people that are colorblind versus not. And we're going to split them up into 2 categories, male and female. And we're going to have a total category too. So we can at least set up this chart and then we'll see how much time we've got. Kind of an ugly, not very straight table, but. All right, so let's say you're doing some sort of medical study, okay, and you find that there are 2 females that are colorblind. 518 were not, for a total of 520 females in your study. 24 males were colorblind. 456 were not. If you add those up, there's 480 men in the study. So then let's do the totals the other way. How many total colorblind people in the study were there? 26, right? And if you add these two with your calculator, you'll get 974. And then what goes here is the same thing that you get vertically for the total and horizontally for the total. So what does this overall total of 1,000 people mean? How many people were we obviously surveying? 1,000 people. Okay. So I want to find the probability that a person is female given that they are colorblind. So what's the formula for given that? It's the probability of both over the probability of which thing? The second thing, right? Colorblind? So with the data in the table like this, we should be able to easily figure that out, right? So what's the probability of both? In other words, what am I asking for? Just the female colorblind people, right? Which was only how many of them? 2, but it's 2 out of how many people total? 1,000, right? And then what's the probability of someone being colorblind in this study? So how many colorblinds total were there? 26 out of 1,000. Okay, so what happens to the thousands just like before? They go away, right? Leaving what fraction that we could reduce actually? 2 over 26, but 2 goes into both of those, so you'd end up getting 1 out of 13. Okay. Notice that if I asked you for the other way, so we're going to do it just really, really fast. So the probability of colorblind given that they're female is not the same, right? That would be the probability of both over the probability of what? Female. So the probability of both is the same, right? The numerator's the same, but what's going to be different? There's a lot more females than there were colorblind people, right? So how many females were there? 520, right? Just look at your totals, over 1,000. And so then we cancel the 1,000 out. And I'm going to go ahead and reduce the fraction too, just in one swoop so we can hurry this along. So it's 1 out of 260, right? So we don't get the same answer when we switch the order of the given that statement. Okay, that's the gist of that.